Okay, so welcome to this week's Origins Colloquium. It's a pleasure to introduce Paola Caselli to this week's talk. So Paola received her PhD from University of Bologna, but with a visit to Harvard Smithsonian as part of it. And then was basically very quickly became a permanent researcher in Chetri in Florence. Was there for a number of years before joining the University of Leeds. As I recall, you were the first woman professor in the physics department, which was great. And then it was 2014 you moved to something like that at MPE, where you run the Center for Astrochemical Studies as one of the groups in Flushing. So great, Paola, we're looking forward to your talk and discussion.
Okay, thank you, Jonathan. So let me start with my usual first slide that I would like to use to basically introduce the topic. So it's a very broad topic. So in half an hour, it would be, of course, I had to select some questions. Yesterday, I had a little bit of a brainstorm with myself and decided, to focus on some questions that I hope are of interest, general interest, and to all of you. And some of you will become very interested and help with this, trying to answer these questions. So, of course, we are all interested, not just me and my group here, we are all interested in understanding how to connect clouds to planets, and in particular to, say, also our solar system, and understand how the physics and the chemistry evolves during these steps. So we go from molecular clouds, a parsec scale, down to fraction of a parsec in these little kernels or cores that are within the molecular clouds where protostars form. And then we start to see lots of things, lots of structures within the disk. And of course, at the same time, we have evolution of the gas and the dust until, of course, we get to regions like primitive, like in our solar system, where we will see there is a rich primitive material that could have contributed to the production of prebiotic molecules and also life. So I would like to start. So the talk is structured just based on what you told me, Jonathan, on say some questions in particular. So I would like to start with the first transition, so from molecular clouds to, say, prestellar core. What I would like to know. What I would like to know in particular, there are, of course, lots of questions. So I decided to consider for the moment a very important point that for me it's very crucial also for the chemistry, because we need to know the structure of cores within molecular clouds if we want to understand how star formation proceeds. And actually the connection between the cores and the cloud is not very well known at all, and it needs very high sensitivity observations. So in this slide here, you can see two figures coming from work done by our former student Spandan Chowdhury, that he used GBT data to look at cores in Ophiuchus. And what we have here are dense cores. Here, the dense cores are defined as regions with, say, subsonic turbulence. So here we have the Mach number less than 1 within these regions. But of course, this is coming from relatively, say, coarse observations. If we look at much higher, say, if we integrate much more the signal, we can actually start to see that the line, this is the typical level of noise that is seen by typical ammonia observations, we start to see actually structure in the line that show us the presence of more turbulent material that connects the various cores, which is the cloud, so ammonia coming from the cloud. And if one uses these new spectra with multiple component analysis, we can see that indeed these, subsonic cores tend to be significantly larger than what we were considering before. So as it is written here, the subsonic component extends up to 0.15 parsec beyond the typical coherent boundaries. And so this transition to coherence, that is also very important to understand how turbulence, dissipates and how material is actually accreting onto the core. It becomes, so the whole picture becomes different, and we need to understand this structure and to use this model to constrain simulation on one side, but also use them for chemical modeling. The other important point that is becoming more and more apparent is that dense cores, I think it is not a big surprise, dense cores are, of course, accreting material, but it's not obvious how they accrete material and actually how much of this material is keep accreting, because, of course, we see, for example, in Taurus, we don't see supermassive stars forming, so there must be some kind of mechanism at some point that will actually stop this accretion onto the core, because then the core will form a star and the star will accrete from the core. So there is, so we are actually very interested in this question, and we are working actively, although there is still lots to do here. For example, in a recent paper by Yushin Lin and Silvia Spezzano and Olli Sipila here, we have seen that this actually work involved also previous work done by Anna Punanova, who actually did the first NOEMA observations of methanol in this core, which is one of the L1544 in Taurus. So we see that there is an asymmetric emission of methanol, and you can see here these orange curves are the NH2, so column density of H2 coming from Herschel, and the color is the methanol map that we got from the ERAM. And this is the larger scale structure of the core, so the cloud where this core is embedded. And here you can see from multiple transition analysis and radiative transfer, considering a Bondor-Ebert profile, as shows here in the green from the Keto and Caselli 2010 paper, we can see that the density at the methanol peak is actually, the volume density is actually larger than what is predicted from this simple Bondor-Ebert sphere. This apparently is actually suggestive of possibly slow motion, slow flow of material coming from this northern part of the core. And we are actively working on this. There are other students. Katarina Geers here is also working on this using other tracers. So we wanted to quantify this because, again, this is very important, not just from the physical evolution of this cores and star formation, but also for the chemistry, because we are creating material that is enriching the core and probably rejuvenating the chemistry coming from the lower density material around. Another important question that is still related to the prestellar cores is formation of complex organics, or the interstellar complex organic molecule. Where do they form? So I just mentioned about the methanol peak. Well, I mean, the methanol peak is seen also, if we look at this course with ALMA, these are beautiful observations by Jorma Harju and collaborators in 2020. And we see again that dense cores that, as you know, in the center are heavily depleted by volatiles, in particular CO, as has been found many years ago. Here we can see that the complex organic, and methanol is the simplest of the complex organic molecules that we see in space, is all around, and in particular on one side of the cloud. Now, we know that we can make methanol, gas phase methanol, like in this case, when you have a lot of CO coming on top of the surface of dust grains, which happens when you have the catastrophic CO freeze-out zone. And this was explained by Anton Basuning et al. In 2017, and also there is work done by Rob Garrod on the non-diffusive chemistry that happens, apparently is very active, even at low temperature. This is another question that still needs to be, of course, totally say work. I mean, we need to work a lot on this from the point of view of the chemistry, because there are still lots of question marks, in particular on the surface chemistry. So it's something that needs a lot of work. However, I would like to point out that it's a very active field, because here we have also work by Anna in 2022, and other people like Scibelli here, Samantha, and Silvia Spezzano, Itaskun, Jimenez Serra, and many other people who have been working on detecting complex organics at the early stages of star formation, so even before, say, protostar come. And in fact, this is an important point that we want to follow up to do this link to later stages of star formation. The other question that we are still working since the 70s, and here I cite Al Wooten and Michel Guélen, who have been a pioneer of this. We need to know the ionization fraction. Okay, we have been measuring it, but there is lots of error bars. We are model dependent. We need more work. We need more sensitive observations. And all this is like written here in these pieces of paper, just to show that it's a kind of old idea, still valid. And of course, we know now much more about this dense cores. We know about the catastrophic freeze out. We know that actually the cores are much denser in the center than originally thought. So we need to go to higher J transitions of these like molecules like DCO plus and HCO plus, or even H2D plus that now is becoming more and more popular. So in 98, we use DCO plus over HCO plus and HCO plus over CO to actually measure the ionization fraction and also the cosmic ray ionization rate. These were data taken in 95, and this is just to show using models what we got at that time. So this is a logarithm of the, say, electron fraction, and this is the logarithm of the cosmic ionization rate. So you can see that there is a kind of a scatter in this dense cores. And this can be understood using, say, propagation of cosmic rays and different spectra of cosmic rays. This is the low and the high, without going into the details. This is, say, using the spectrum of cosmic rays coming from the Voyager, and this is from, say, using higher values to actually reproduce these Indriolo and McCall values that have been measured using H3 plus. And here just seeing how they also cosmic rays don't just, of course, ionize and maintain this level ionization that is very important for the dynamical evolution of magnetized core, but is also important for they're also important for UV, because within high density regions, you have UV photons produced by cosmic ray propagation in dense gas. So this is important. H2D plus, as I said, is very bright in these regions because it is has been shown many years ago that H2D plus become very strong if you have a heavy say large amounts of depletion of volatiles, and has been used recently, and it is found to be a reliable tracer of electron fraction, as Stefano Bovino and collaborators, and including Sabatini and also Elena Redaelli, have found. Of course, we need to be careful also here, because if we go to very high depletion, you have a super deuteration. So H2D plus can be transformed in D2H plus or D3 plus. So we need to also be a bit careful and mindful about this tracer of electron fraction. In any case, using multiple transitions of, for example, HCO plus and DCO plus, Elena Redaelli, using also with the help of Olli Sipila, chemical modeling of deuterated species in cold regions, and the help of Marco Padovani for the propagation of cosmic rays, we were able to actually reproduce lines that were observed with different. So here we show different. So this is the radius, and this is the cosmic ionization rate for H2 molecules. And here there are different profile for the cosmic ionization rate. So this is the typical, or say fiducial value, 1.3 times 10 to the minus 17 per second. But also we have the Voyager considering attenuation within the dense core. And this is the high, so with the higher flux of cosmic rays. And what Elena found is that actually it's the best reproduction, so we don't need a significant correction factor considering the models, is with the low models. So high models are not able to reproduce the observation, so we can exclude this large, say, cosmic ray ionization rate, and we are sitting at around, say, 3 times 10 to the minus 17 per second, which is exactly what the Voyager found. And using this, the red curve then gives you the new updated XE. So this is the electron fraction profile within a prestellar core. So we can go ahead with this, but you see, I mean, it's time consuming and we need a lot of observing time to do this properly. Just a little advertising also to a beautiful mapping mosaic that was done by Jaime and collaborators here, again, to reveal the electron fraction using the CO plus and H13 CO plus in a region, southern region of NGC 1333. Here you have protostars with the star symbol, and this is a 96 pointing mosaic, okay, done with NOEMA. So it's a huge effort that was carried out by Jaime. And what they found is that the ionization fraction here increases nearby protostars, and it is considering this kernel density estimate, KDE, you have a peak around minus 10, so 10 to the minus 6.5, which is relatively high. And there is also seems to be a gradient from the north to the south, where there is more activity here, protostellar activity. So the other interesting thing that Jaime found is that the electron fraction seems actually to increase with the density, which is, of course, if you take a starless core, this doesn't work. We typically have trends that go down with the density, as also shown initially in the 80s, in 89 by Chris McKee. So this is due to the fact that you have a production of energetic particle within, say, nearby protostars. So in fact, it can be seen that the ionization fraction peak here at 10 to the minus 16.5. And you can see here in this map that show the ionization fraction that you have a lighter color, so yellower color nearby protostars. So we are saying that there is a local production of cosmic rays by protostar that was already found by other people like Cecilia Ceccarelli work in 2014, Padovani in 2016, actually he modeled this propagation along shocks and outflows, and also of course Stella Hoffner has done a lot of work also on this. This is important because if you have a large ionization, you can actually influence the structure of the future generation of protoplanetary disks, because if you have larger ionization, you can actually, it becomes more difficult to say, produce form disks, as far as we know, using magnetohydrodynamic simulations. And this is shown in this figure from Kufmeyer et al. 2020, where we have different values of the cosmic ionization rate, starting with a low mass core and looking at the evolution. You can see with the high cosmic ionization rate, you end up with basically no disk, while, yes, like 10 to the minus 17, you can actually form a rotationally supported disk. And cosmic rays are super important also for the chemistry, as we all well know. And in particular, Chris Shingley-Decker has done a lot of work on this. And while he was a Humboldt fellow here with us, we work on the sulfur problem. And he found that if we take into account this irradiation from cosmic rays, you can actually transform H2S, so the usual, what we think happens once the sulfur atoms are landing on surface of the grains, they get hydrogenated, like oxygen forming water. We have H2S for the sulfur. But if we implement this irradiation chemistry, you end up with a lot of sulfur. This is abundance as a function of H2 molecule, as a function of time. This is with respect to H2 molecules as a function of time. You see that you have lots of S8 forming, which is the most stable form of sulfur. Interestingly enough, and linking to our solar system, allotropes, so these chains of sulfur, have been also detected in the comet COMA, the 67P. And this is the paper that showed this interesting. So it could be that the sulfur becomes, there is a larger reservoir of sulfur in these chains. These chains are really refractory, so they are like attached to the surface of the grain, and then they stay there until they are delivered to the, say, planet formation. Another important point is that also other molecules are affected. Of course, as Chris Shingledecker has shown in the past during his PhD work with Eric Herbst, they found, in fact, that with the cosmic rays, you can increase also the abundance of organic and complex organic molecules. So let me go to the next step. So from prestellar core to protoplanetary disks. I know that Dominic has given a talk recently, so I don't think I need to introduce to you the streamers, but I will definitely talk about those because these are the important points. Is there a question, or sorry, I heard some.
No, I think it's just a
okay. Okay, sorry. So one question I have, and I would like to answer sooner or later if I get some ALMA time, is what is the evolution of this core, prestellar core, which we call it kernels. So with ALMA, now we are able to see actually the very central region of dense core, and this is the mosaic that we did and published in 2022. And I how these compare to simulations. We did that in 2019, comparing the, say, continuum flux, and finding that indeed it is consistent with the non-ideal MHD simulations of core contracting along magnetic field lines. And we can reproduce the continuum. And now I wanted to understand the kinematics. And for this, we have the neutral here, but of course we need a bit higher, even higher angular resolution and ions as well as neutral to do a little bit more detailed work. But kinematics is coming up. That will be the next work. And so the central part of the course are not just important to understand the first steps toward the formation of the so-called pseudodisk from Galli and Schur 93, but also, say, the formation of protoplanetary disk. But it's also important as a reservoir of organics, because it's within this course that these kernels, that we actually see almost complete freeze out. So you get all your volatiles onto the surface of dust grains, as it is shown here with our, say, this is only CPLA chemical modeling showing depletion as if this is the abundance of deuterated ammonia as a function of radius within the core. And you see that you have almost complete depletion within the central 2000 AU. And if we don't do this, we cannot reproduce the spectra that we get with ALMA. So this is important because, of course, it's the next step. So these are all within this flattened structure, within this pseudodisk, we will get the initial ingredients and conditions for the formation of protoplanetary disk. And then some of this material will be included into planetesimals. And of course, this is what now we are trying to understand with JWST. And just for a little example, there are now more and more papers coming out from the JWST, for example, Ice Age team. And it's true that we started to see evidence of complex organics, in particular in this region between 7 and 8 micrometer. There is still, again, a lot of work to do, both observationally from the point of view of JWST observations, but also laboratory, to see if indeed some of the features that are seen toward this dense cloud material are indeed features coming from, say, acetaldehyde or ethyl alcohol or acetone that is here. So still lots of work going on. This flattened structure of prestellar cores, of course, are not isolated from the rest of the cloud, and they're still accreting material. And we see evidence that of this material keep accreting onto the central part of the region with the streamers that was measured with HC3N and using NOEMA by Jaime Pineda in 2020, and followed this by many other papers that show this continuous accretion. You can see here from a larger scale, the little, say, class 0 protostar here that is surrounded by a huge amount of material. And some material is actually flowing from a northern region that has been recently discovered by Taniguchi, Kotomi, that found with the Nobeyama telescope a reservoir of this stream. Understand the origin of the streamer and how much material they're actually injecting. And actually, if they are affecting the structure, so this is a work that has been recently submitted by Carolina Giza here at MPE, showing, for example, a very famous system at 1448 North that show two protostar. This is a multiple protostellar system. And here, what she find with NOEMA and the larger program, Prodigy, that we are, say, leading together with Heidelberg, we have ridges, we have streamers, and what about trying to connect these streamers to actually the inner disks that are forming? There are these beautiful images from ALMA by Reynolds, John Tobin, and collaborators that show evidence of gravitationally unstable disk. But what about if these streamers are actually contributing to the asymmetries of these disks and then mimic what, say, gravitationally unstable structures? For example, another example is this one from Maria Jose Maureira, Munangon, and Jaime Pineda, where this is the famous area 16293 minus 2422. If we focus on the A system, which is a triple system, so this is the whole thing, sorry, it's a triple system, this is a double binary system. And with ALMA observations in the continuum at very high angular resolution, you can see actually hot spots around this binary system. And these hot spots coincide, at least some of them, with the peaks in complex organic molecules. So there is also this interesting, say, comparison between the presence of shock heating and complex organic molecules, and this could raise the question if this, what we call a hot corinos, are actually coming from shocked material. A zoom in what is this IRA 16293b, which is in the north, and this is where, yes, Jorgensen has done lots of work because he has the large program PILS, where there are lots of, this is a prototypical hot corino. And so Zamponi here at MPE with Maria Jose Maureira, these are very high angular resolution observation, is still in the continuum at 1 and 3 millimeters, showing that indeed that you have a hot core temperature that can go beyond the 300-400 Kelvin. So of course at this, and with the 3 millimeter brightness temperature larger than the brightness temperature at 1 millimeter, showing that actually if you go deeper into the disk, you get hotter material. And this say, hot disk can be reproduced with simulation of, say, gravitationally unstable disks, as we have shown in this paper here. But of course, you can also produce these hot spots by considering this accretion of material from the envelope or the cloud. And of course, this triggers other questions, because at this temperature, you don't just say evaporate some of the ice that you bring in from this, say, reservoir of ice from the original prestellar core, but you also can process the dust, because this has been discussed several times by Van Hoff and also Pune and Azari, showing that at this temperature, you actually go beyond the so-called soot line, so you can have the refractory carbon coming back in the gas phase, enriching, of course, the chemistry with a lot of carbon from the grains. So in these regions, you can actually, so if we go a little bit beyond the class 0, so we get closer to the class 1 now, and this is the work by Dominic. And here, as you know, this Nature paper showed that even at these early stages of evolution, you can see rings and gaps. And now the question is how these rings and gaps are forming. And one of the possibility, again, is this incoming material from the envelope and the cloud. And this is something that Dominic is actively working on, is preparing this work showing this accretion of material from the H13CO plus 4-3 transition. And then also there are more papers like Flores et al. And also a new paper that has been recently submitted by Linda Podio from Arcetri, showing indeed the material coming in and enriching, in this case of Linda Podio, deuterated material. I'm not going into that. The streamers are also found in later stages. This is work by Felipe Alves, but involving also Ilse Klebs and Miguel Girard, showing that even in the class 1, class 2 stage, we still see filaments of material that are, say, the kinematics is consistent with this gentle accretion of material still on a disk, that where there is not just a star forming, but apparently also planet forming in these gaps that we see. This is a disk seen at John. So let me finish just showing now the last steps that, of course, are the more, how to say, complex, because we wanted to then go from disk, protoplanetary disk, to planet-forming disk, and then to understanding the terrestrial planets, primitive material in our solar system. So of course, here we enter, a huge field that, I'm not going to just briefly mention some things that are very much of interest for us. And one of these is the comparison between, say, a material that we see in prestellar cores and young protostars with material that is seen in comets. And this involves complex organics, but also material that is fractionated, like deuteration, like it has been, say, studied by Maria Drozdoskaya and collaborator. And Wiebke Riedel here, she's working very hard on the modeling of this deuterated material on the surface, in particular methanol, but also simpler species. And then, of course, there is a lot of interest in connecting through the, relative abundances of fractionated material. And I'm saying in particular, deuterium 15N, but also carbon-13. And you can find more, very extensive review papers in the PP7 chapters by Ceccarelli and also Nomura on these points. But the interesting thing is that so far it seems both the deuteration but also the complex organics seem to show that the volatile composition, as I wrote here, of cometesimal and planetesimal has to be partially inherited from the pre and protostellar phases of evolution. We see a lot of the similarities. So some of this material, despite probably these hot phases during, as we saw before in say protoplanetary disk, young protoplanetary disk, some of this material must be kept inside rocks. Maybe this means that these dust grains coagulate relatively fast, so some of the material is protected within larger pebbles. And also you have to keep accreting material from the cloud where you still have ice coming in. So there are multiple stages that we need to take into account when we study the chemistry also of disks. So, of course, just to finish up and to keep motivating everybody, because I think this is something that we are all interested on. And this is really to link these volatiles and ices to what we see in primitive material in our solar system. Now there are all the return missions from, say, Osiris-Rex, so from the asteroids, a couple of asteroids. So it will be super interesting to actually understand how, and if there is a link from, say, the simple ices that we start to see now with JWST and the prebiotic chemistry that is found in primitive material, in particular in carbonaceous chondrites, where there are lots of ingredients, including amino acids, fatty acids, and all the bases in RNA and DNA. So this is my last slide, just to say that there is a lot of work to do, because so we need to start with realistic modeling of, say, clouds and then formation of disks, and try to really link the dynamics and chemistry during these phases, because this is also super important if we wanted to understand, for example, for the exoplanet community, how this early material has, in a sense of, we know that it's affecting the geo and the biochemical evolution of habitable planets. And this is, in fact, something that, so the, composition of pebbles and then planetesimals, etc., are, of course, of very important for also terrestrial planets that we know have multiple phases of accretion during their evolution. And this is the work that I always like to cite, because it's a beautiful paper by Pierce and collaborators, including Ralph Pudritz, where they show indeed that starting from the composition of this primitive material in an early Earth type of planet, you can actually form RNA molecule in a very short time. By short time, I mean 200,000 years after the moon forming event, which is nothing compared to, you know, compared to the age of our Earth. So still lots to do, but I think we are all super motivating in trying to understand this and link to also origins of life. That is something else completely. Okay, so I hope you are interested in some of these questions. If you have more questions, please don't hesitate to ask.
Great, thank you very much. So we can open things up for questions, and maybe we should, because there's lots of different topics covered, maybe we should structure the discussion a little bit roughly in the order of the talk. So maybe roughly core definition and prestellar cores, and then cosmic rays and disks, and of course the astrochemistry comes along with it. But you know, people should raise their hand in Zoom or here.
Should I switch off the?
I think, well, you may want to show slides in response to questions.
Okay, yeah, that's fine.
Yeah. So while I'm waiting to see some hands raised, let me come to the first point you were making about the definition of cores. So can you remind us how observationally you are defining cores? You were saying this subsonic.
Well,
is it the region that is subsonic that extends beyond a previous boundary, and how is the previous boundary defined?
Well, I mean, the boundary that I showed, it'd be nice to see if I could actually go to the slides without having to go one by one. Maybe it's better if I stop sharing and then I say share again, because otherwise you see lots of going back and forth. Are you still seeing the slides?
No, you stopped sharing, so just restart.
Okay, good. So let me just go back to this slide here. So this is the work by Chowdhury and collaborators here. I hope this takes too long. Yeah, I shouldn't do this. Do you see the slide?
Yes.
Okay, so this is so it's a hard question, no? Where does the core stops and how it is connected to the cloud? We cannot tell that unless we have a super sensitive observations. This is definitely something we have learned in the past, because and actually ammonia in a dense environment is a very good tracer for this, because you can actually see ammonia, for example, in Ophiuchus extended over a large scale. This is different from what we see, for example, in Taurus, where ammonia is kind of concentrated within the cores.
So in terms of a physical definition, is it material that is gravitationally bound to the core? And do you proceed outwards? But how can you really tell?
Yes, so here a general definition that was taken also from previous work is using the Mach number, because we know that dense cores tend to be coherent structure where the turbulence is actually at a very low level, so thermally supported. So we have a subsonic line widths here. So these lines that you see here, this define Mach equal 1. And this is the definition that was given, because, you need, in the past, the size of the core was defined as the full width, so basically at the 50% contour level. But again, that is also some kind of arbitrary. What our point here is really, we wanted to understand how these cores are connected to the cloud. There is some more data that we ask also with the VLA and the GBT to do, actually mostly here is the GBT data to go very, very deep in the cloud to see if there is a connection, say, to this core in particular, this Ophiuchus HMM1, to really understand how this connection is done. Because, when we use also the chemistry, we assume these mono-Ebert spheres, which
there are three related questions at least that come to mind. So one is, as you know, there are models of core formation which involve supersonic turbulence behind shocks, which I've never particularly liked. But can you test those models? Because they would claim cores form in a post-shock boundary region, so there'd be quite disturbed kinematics around. There'd probably be chemical signatures of the shocks. So that's one question. I'll do a quick comment on that.
Well, because I tend to forget things very quickly, so let me answer. So here we don't have much so far to test. So the only one object that where we have some data on this methanol and we can actually measure the density there accurately, because we have multiple transitions of the methanol, which is in particularly showing enhancement on one side. I mean, we can say that there is probably evidence of, say, accretion of material onto this core. We don't see rings of hot gas around cores, which I think if you have like a shock produced or, a very turbulent environment, I would expect to see relatively high temperatures around these cores. And this is not seen with the data that we have. Even the methanol is cold. So there is a little bit of enhancement in density and slight enhancement in line widths, but you can reproduce this with very slow flow of material. You know, you don't have a very big gravitational well here, so you don't expect to have a lot of, like in these hubs and filament system that you see in high mass forming regions. Here, everything must be much more gentle, but we have not yet quantified. This is a difficult test, I think.
Yeah, I'm still waiting for people to raise their hands in the Zoom or here. So, but in the absence of seeing that, I'm going to continue. Then the time scale then related here, obviously chemical clocks or you know, the dust evolution clock maybe. Or do you have a way to order things in some kind of time scales, or can you tell if the prestellar core is younger, or do you rely on physical structure being more concentrated, or perhaps you can comment a little bit on the time scales.
So, yeah, the chemical clock, I think, is hard. It's very hard. I mean, we have shown that there is a new paper with Eric Keto and also say Jonathan Rawlings, where we show that basically the chemistry that is, especially for these say simpler species, it's consistent with being like at equilibrium in this dense cores. It's very hard to get a chemical clock, a reliable chemical clock. And it's also hard to say because you can have say lower density cores, and of course we see like what we call starless cores, so relatively low density, constant temperature, and then we have the prestellar cores where they have these centrally concentrated structures and say they have low temperatures like 6 Kelvin in the center. There are a few of those, and we are actually working on increasing the sample. But of course, these objects are very, they have a very short time scale because they are going to form a star soon. So I think from this point of view, it's really hard to actually chemically say something because, you know, you have, for example, more deuteration that tells you that you have a more dynamically evolved core. But I'm not sure if that is older than a lower density core that may be sitting there since a longer time. It's just that it doesn't have the environmental conditions to accrete more material and become, say, centrally concentrated and go. So it's very hard because this is linked to the initial conditions as well. So the initial abundances that you have, do you start with the same initial conditions? Is the say your cloud is more or less homogeneous around the core? So it's the is let me put it in this way, maybe it's simpler and more to the point. Chemistry, you cannot disentangle with the density, okay? So if it is denser, it could look older, the chemistry, but actually just because it's denser, so the chemistry proceeds faster. So we need to be careful, just I think collect the data to understand the dynamics, the chemistry, forget at the moment the chemical clocks, and just put things together, and then later, this is an option, I would say, a luxury that we can get from the astrochemistry, but I don't think we are there yet.
Okay. Any other questions? Yeah, let's go to cosmic rays now then. So Gina has a question about the cosmic ray part.
Yeah, so I was wondering, when you showed the analysis with the finding 10 to the minus 17, right? The ionization rate. And I was curious if you did this kind of analysis, it seemed more complicated than modeling. If you can do that for the other areas or cores or clouds where they found the higher rates, would those results change? Like with the tension between Voyager and the other clouds.
Yes. I mean, yeah, this is so I don't know if I understood correctly because I had to interpolate a little bit. So you are asking about the low density, so the cosmic ionization rate that is measured in more diffuse clouds. that
Yes,
it
yeah.
looks like it's very high, and this is coming from the H3 plus data. Yes, actually, I didn't show it because we have two papers that have been submitted recently, and this is work done by a PhD student here by Marta Bonsleva and Alexei Ivlev in particular, in collaboration with David Neufeld and also Nick Indriolo, that Nick is the one who actually measured it. So we have actually some new data on that, and indeed, there was a problem in the previous determination of cosmic ionization rate, in a sense that the main problem was the assumption of density, volume densities of diffuse clouds. Now, with the help of, say, data, especially from Gaia, that it was able to get more reliable volume densities, we now have new values of the densities of the diffuse clouds that is also coming back. This is work that has been submitted, so it's a little bit we will see, but we also have from David Neufeld a reelaboration, say a recalculation of the volume densities in diffuse clouds based on the C2 molecule that was used in the past with say kind of not correct collisional coefficients. Now we have the newer collisional coefficients, and also with the C2 molecule, we can actually so the volume density agree also with what Alexei and Marta found.
I understand. What is the revised cosmic ionization rate in the diffuse ISM then?
Well, we should look into the paper. There is a bit of a spread, but it's significantly lower. So we talk about, between a factor of a few to a factor of 10 lower in diffuse clouds. And actually it agrees with the Voyager data.
It's more like a few times 10 to minus 17 back to that level.
10 to the minus 17 for the ionization rate of H2 molecules. Yes, so it's a good question, but I didn't prepare a slide of that because I didn't want to kind of first of all spoil the results, but the papers have been submitted, so hopefully we will get a positive answer soon. So yeah, it will be revised. It will be, everything will go down a little bit. And then the question is how we can measure accurately enough, the cosmic ionization rate within quartz. I show you the Reda Elliott et al. Paper that indeed is consistent with what we have in the diffuse medium, because she needs 3 times 10 to the minus 17, and then we can reproduce the data as I see Brandt.
Yes, Brandt has a question.
Right.
The expert on cosmic rays.
Yeah, it was just to follow up on the point from the new results from David, because I just saw the results at a conference not that long ago. So it takes the diffuse results from Nick and Driolo down by a factor of 3 or so. So from 2 times 10 to the minus 16 to just below 1 times 10 to the minus 16, so 6, 7 times 10 to the minus 17. But in fact, the problem is even worse, because for diffuse hydrogen regions, new chemical data has shown that those should go up by a factor of 3. So in fact, the gradient now from kind of the hydrogen envelope to the H2 envelope is much steeper than I think any models, including Marco and I's models, predict. And then this begs the question of, well, what is Voyager tracing, right? Voyager's in diffuse hydrogen gas, not H2 gas. And so, in some sense, comparing to Voyager is always a bit fraught, because Voyager is not in any of these environments. And so, but I think right now the problem is there's a huge amount of spread in basically all the observational data. And so I think this is where we just need better modeling, because is the spread systematic from noise? Is it just being in the galaxy?
Yeah, I think for the say diffuse clouds, we have a much better understanding, I think, now with this new data, and also from C2 and the Gaia. For the atomic, I don't totally agree with what you say, because I think even there we need to reconsider the densities that are considered. Because we are actually measuring zeta divided by n. And so it is super important to have n. And now we learned that. And so I would say maybe you're right. I mean, I'm not saying you're wrong, but we have to redo a very detailed analysis
Yeah.
also in the atomic. I totally agree, because that then will actually be very important to understand if there is any, how to say, any losses or, you know, any propagation effect that you know better than me how, but it will be very important to do that, definitely. So that will be the next step, using this OH plus data, and also make sure that there are no say uncertainties or say small error bars also in say collision coefficients and other kind of measurements also for the density. And this is something that yeah, we are also interested in working on that yeah, as a next
So
step.
this effect, you know, we're working on the galactic center in some projects, and you know, one always hears that the cosmic ionization rate in the galactic center is many orders of magnitude higher, you know, around 10 to the minus 15 or something. But does any of this affect those estimates?
Well, we don't have the estimates of the density. So the work that has been done in this paper by Marta and David, we are focusing on the neighborhood, in our neighborhood. So we are focusing within, you know, say Gulf Belt and you know, the nearby regions, less than 1 kiloparsec. If you go farther out, the density, so the error on the volume density estimates becomes much larger, and then it becomes more, say, critical to have a reliable estimate. But you see, I mean, we were discussing, in fact, with Alexei recently, because we found a paper, there was a paper recently on AstroPH with Stefano Gabici as the last author, saying that they think cosmic rays cannot be the only source of this strong ionization in the galactic center. But it's also true that the density, the volume densities are probably not well known. So maybe, you know, we have to scale them down. I'm not saying that now this is a general rule, you know, but we need to be super careful about the physical conditions of the cloud that we are talking about.
Well, you showed briefly the constraint of the cosmic rays comes from this, you know, PCO plus and HCO plus. Do you have a constraint in the center of the core where you have all this freeze out, this catastrophic freeze out? Does that, you know, there are desorption processes that depend on cosmic rays.
Yeah, it's really hard. So you have to be, so you are very much model dependent, because you can still, so there is this catastrophic CO freeze out, which of course affects also HCO plus and DCO plus. You're not, it's important when I say almost complete freeze out. It's not a total freeze out, because you still have some low abundance, you still have it, which I think is good, because it then prevents your line to become optically thick. So if you have ALMA, and this is, you know, trying to get some time there since a long time to go in the center to look at these lines, high J transitions of say DCO plus and also other like N2H plus, N2D plus, etc., to map this region and connect to the model. This is super important. So that's why I say you need to have a good model of the source. You need to follow the radiative transfer as well as possible, because otherwise you can be wrong by, you know, or an order of magnitude. So you really need to have as many lines as possible to be able to constrain your chemistry and radiative transfer. We know this from the previous work, and mainly actually Olli Sipilä here has done, put a lot of effort on this, and also Elena Redaelli, etc., and other people. So we know that this is super important. We need to be constrained with the model, by the model. And
we're almost at, well, we are at time, but let's take one from John Black. Next, we just go a few minutes over here. Please go ahead, John.
Right, well, nice to see you.
Yeah, good to see you too. I was fascinated to hear about this recent work on the revised C2 densities, of course. And it just occurred to me in response to, I think, the point that Jonathan raised about the central molecular zone in the Milky Way, where there are H3 plus based ionization rates, that those observations also include measurements of H3+ in excited and metastable states that give a fairly good handle on the density already in that
Okay.
component of the gas. But then there's also an intriguing possibility of getting improved near-infrared observations of the C2 toward the same background stars used for the H3+. And so if you're interested, I could send some suggestions about the spectroscopy.
Yes, definitely. That will be very good. Thank you, because of course we are all learning, and yeah, we need to understand better the problem. Maybe I mean, if I will ask David, because David is the first author on the C2, but it'd be great if you can actually have a look at the paper.
Oh, I'd be very interested to see it.
Yes, exactly. I mean, you have been working on that since a long time. So I will ask David to send you a copy, and we will be very happy to have your comments, of course. And yes, if you can send me this data, this information that you mentioned, that would be great.
Very good. I still have plenty of more questions on the discs and so on, but I think we're going to have to call you back another time, Paolo, to discuss those. So I think we should wrap up now, but let's thank Paolo again.
Thank you for listening.